Welcome back to another Forge College Explainer. So if you were with us for our previous lesson, implementing client interaction for program calls, you already know exactly how to build a client that talks to Solana programs. But today, today we're dealing with reality. We're going to build on that foundation by learning how to fix and tune your Solana cross-program invocations, or CPIs, when they inevitably break. Because let's face it, they absolutely will break at some point, and we need to know how to fix them. We've all been there, right? Let's just acknowledge the developer's pain for a second. You built the invocation perfectly, you double-checked every line of your syntax, you turn the key, and boom, your terminal just spits out a wall of red error codes. We all know the old joke that if it compiles, it works, but honestly, that is a complete illusion when it comes to runtime execution. A successful compile really just means you've earned the privilege of discovering your runtime errors. So what gives? Why did it crash? Let's find out. Here's our repair manual index for today. First, we'll look at the anatomy of a crash. Then, we're unlocking your diagnostic toolkit, followed by fixing common CPI failures, optimizing program interactions, and finally, the ultimate debug report.
Okay, let's jump straight into section 1, the anatomy of a crash. To successfully diagnose a CPI crash, we first have to recognize where the system is actually the most fragile. The most frequent points of failure aren't usually some massive complex logic bug. No, they're those tiny but absolutely critical metadata flags on your accounts. A CPI failure is most commonly caused by a mismatch in deciding exactly which accounts are passed, which of those are marked as writable, and which absolutely must be signers. It's kind of like bringing the wrong ID to a really strict bouncer. If the details don't match exactly, you're not getting in. If there is one golden rule you take away from this entire explainer, it's this blueprint standard right here. Always map the transaction's message.accountKeys sequence to the callee's expected account info ordering. Your transaction keys, the array of accounts you're sending from your client, must perfectly align with what the receiving program expects to see. If the callee expects account A and then account B, but you send B and then A, the program will panic, period. All right, moving on to section 2, unlocking your diagnostic toolkit. When your transaction fails, please don't just stare at the generic error code on your screen. It won't help you. A crucial property you need to investigate is meta.log messages. By fetching the confirmed transaction using your TypeScript client and actually examining that meta.log messages array, you get the actual structured logs directly from the validator. You can instantly see if your target program was even reached before the whole thing failed, or if it just died in transit. But here's the catch. To get good logs, you have to write good logs. You need to instrument the on-chain program with targeted MSG macros. Adding these MSG macros in your Rust code acts exactly like placing diagnostic sensors deep inside a car engine. You really want to place them right before key branches, like just before a signer check or a PDA seed verification. This feeds direct, highly readable outputs straight into those client-side logs we were just talking about. So, with our diagnostics running and our sensors placed, let's get our hands dirty in section 3, fixing common CPI failures. You can think of this process as your ultimate mechanics diagnostic checklist, where mapping exact symptoms directly to their likely cause. For instance, if you see custom error, your initial check should be your account to ordering. Is it wrong, or is a signature missing? If the program just flat out failed to complete, you likely exceeded your compute budget or hit a panic, so inspect your logs for that. And if there are absolutely 0 program logs visible, well, that usually means a basic signer check failed before the program even had a chance to start executing. The ideal debugging workflow really breaks down into 4 super simple steps. Step 1, reproduce the failure deterministically. Step 2, add those client logs and MSG macros. Step 3, inspect your account ordering. And finally, step 4, apply your targeted code fixes. By following this exact step-by-step procedure, debugging transforms from a really frustrating guessing game into a highly systematic and, frankly, super satisfying engineering process. Okay, so we fixed the engine. But in section 4, optimizing program interactions, we don't just settle for working. Let's talk about efficiency, because leaner is always better. To put this into perspective, an unoptimized setup might pass, say, 12 account keys, including a bunch of redundant read-only accounts that you don't even need. But a truly optimized version, it passes exactly the 10 necessary keys and nothing more. By trimming out those extra accounts, you drastically reduce the transaction size, you cut out redundant compute work, and you shrink the surface area for potential metadata mismatches.
Furthermore, optimizing isn't just about speed, It's about stability. And that brings us to resilience patterns. You absolutely need to make the client handle transient confirmation failures by actively checking the status and retrying idempotently. Adding these bounded, logged retries ensures that intermittent network hiccups or sudden RPC drops won't make your entire end-to-end flow look flaky to the user.
Finally, let's wrap things up with Section 5, the ultimate debug report. We've done all the hard work, but now we need to record it to prep for the upcoming capstone integration. In our curriculum, your debug report is basically the artifact of your success. It requires you to systematically document what you've actually done. You need to identify 2 distinct failure causes using your logs, apply the fixes, and show concrete evidence of a reduced failure rate, and then demonstrate your optimizations using measurable before and after account counts. Remember, if you didn't document it, it didn't happen. So let's bring it all together. The crucial takeaways for today are, number 1, always check your blueprints for account alignment. Make sure you map your message keys to the expected account order. Number 2, use targeted on-chain logs and client-side message logs to pinpoint the exact crash site. And number 3, trim the fat. Optimize your code by removing redundant accounts and always validate those improvements with hard metrics. Which brings us to our final provocative thought for the day. Your CPI is fixed and it's beautifully optimized. But how will this robust foundation scale when it's finally integrated into the massive, full application deployment for your capstone? Because that is the real test. As you think about how you're going to tackle that challenge, remember to visit forge.college to dive deeper into this and tons of other incredible Web3 topics. This explainer was proudly made by Forge College. Keep building, keep optimizing, and we will see you next time.